Okay, so we're going to try and talk about angular momentum today. Let me get me up there. So we're going to try and talk about angular momentum, and I need to remember to hit the pause button on this broadcast when it comes up. Just a second. Get a clean whiteboard here. All right, there's that. And let me do this here. All right. So, all right. So the textbook definition of angular momentum looks like this. And again, this is on page 83 in workbook volume 2. So if you want to have that open to follow along, or in case that inspires some questions, page 83. All right. So in this case, I just want to start with a point particle. It's moving some direction. And there's an arbitrary point of reference that I'm going to choose to call the pivot. Okay. Now there's going to be a vector that goes from the pivot to this particle that's moving. Now there's an angle in here. I'm just going to call that phi. Now in this case, I want you to, this is not the same as the last chapter where we had a force and an r vector. Okay, this is a velocity. So I'm going to draw a line through that velocity vector. And I want to be clear, this is not the line of action. I would call this the line of motion. A line of action runs through a force. This is not the same thing. The r vector, if you look, is defined the same way, from the pivot to the point of interest. Here, the point of interest is where the object is located. In the last chapter, it was where the force is applied. Very different. Now, it turns out we could do the same thing as before by creating the perpendicular bisector. We draw a line that goes from the pivot to the line of motion that forms a right angle. This is called the perpendicular bisector in some math class. This is sometimes called r perp, just like last time, r perpendicular to the line of motion. And notice in this case, we're going to get some size that is r sine of phi. If this is a right triangle, if this is a right angle, this is a right angle, this is a right triangle, opposite, sine, etc. So sometimes we're going to look at this definition. Angular momentum is the symbol L. And instead of being just the regular momentum, it's r cross p. So let me actually color code this. You take the normal momentum vector and you cross product it in this specific order with this r vector. So notice this would be r crossed with, does anybody remember what momentum was?
Mass times v.
Yep, mv. And so notice you get a cross product. To be clear, the order matters. If you switch the order of terms in a cross product, you get a minus sign. Case in point, I hat cross j hat equals k hat. But j hat cross I hat equals negative k hat. If you remember the wheel of pain, that will help you remember the minus signs. So this is when we're doing cross products, as we are in this chapter and the last chapter, knowing the wheel of pain can simplify things. I goes to J goes to K. If you're going the right way around the circle, positives. Wrong way, negatives. Okay. So now in this case, I thought, well, let's stick in some numbers for this and just see what this angular momentum turns out. So let's say in this case, let's say that r is 3 in the negative I hat plus maybe 3. How How about 4 in the j hat? I don't know. Now, obviously, this has units of meters. I'm running out of room here, so maybe I should rewrite it. -3 in the I hat plus 4 in the j hat in units of meters. Okay, that's supposed to represent this. 3 to the left, 4 up. Sorry if it's not to scale. My bad. Okay, and now what is this velocity vector? Well, let's assume in this case the velocity is, it looks like it's about, let's say, 6 in the I hat plus maybe 1 in the j hat in units of meters per second. I'm just eyeballing it and making up some stuff. So it's not perfectly horizontal. There's a little bit of up to it. All right. And then let's say the mass of this thing is just 1.0 kilograms. All right. So forgetting the sig figs, let's just say it's 1 kilogram. All right. You could take these numbers, plug them in here, work out the i's cross i's drop out, the j's cross j's drop out, the I cross j gives you k hat, the j cross I gives you negative k hat, and you could get an answer when you plug into here. Notice, what direction is it? When you do all the math on this, what direction do you think the final answer should be? Before we stick in all this junk, let's use the original definition here. First vector, use your right hand and line it up with the first vector. There it is. Curl to the second vector. Which way does my thumb point?
Into the page.
Into the page. So if we assume that this is I hat, this is j hat, and out of the page is k hat, always check it. I goes to j goes to k. What is the direction of the angular momentum for this particle?
Negative k hat.
Negative k hat. So we know the answer should be negative k hat for the direction. This is a way you could check your work. Now, what does that mean? Remember, the thumb is like the axis of rotation. So you got to do this right hand. If you put your thumb in the pivot, see how my thumb, if I lock my thumb in the pivot there and I start curling, this corresponds to clockwise. That makes sense. So that's what the direction means here. It's the direction of the axis of rotation about this point. Now, one of the things that's a little weird about this is this object rotating or is it moving in a straight line? If we just shoot it out of a gun in space, there's no actual object here. This is just going to keep flying in a straight line. And yet I just described it as going clockwise. Here's the thing that's weird about it. As this moves in a straight line path, check this out. This radius vector, will this red arrow get longer or shorter as it goes that way?
Shorter until it
Shorter. Yeah, until you get to here, and then it'll get bigger again. What about the angle? As you get closer to this point right here, is the angle getting bigger or smaller?
Smaller.
Bigger. This angle gets smaller, but that angle gets bigger. It gets closer and closer to 90. Agreed? So right here, it looks like it's about 45. Right here, it's going to be close to 90. Is that good, Alonzo?
Yeah.
Yep. And so what's weird about this is this number shrinks, this number gets bigger, which makes the sign bigger. And as a result, this term right here actually stays the same. Do you see that? Our perpendicular is the same for any point in the line of motion. So sometimes what we do is we then say, rather than go through all of this mumbo jumbo, what we could do is just figure out R perpendicular times MVR. So what we do is we say MVR perp in this direction, and that's easier than doing this full cross product sometimes. Let me check the chat here, see if I'm behind. Okay, Mark, did I get your question addressed or not?
Yeah, you did.
Okay, yeah. So this is now obviously we could do scenarios where it curves as well. And then it would be more complicated, but we'll worry about that in a minute. All right. So now this is what works for 1 point particle. Now, let me rephrase this in a different way. Or any other questions before I erase all this? Obviously, you could punch in these numbers and do the math. We're not going to right now. All right. Yeah. Now, in practice, sometimes getting R perpendicular is a little tricky, right? Look at this. You'd have to do some geometry and use SOHCAHTOA and stuff. You'd have to think a little bit to figure out what R perpendicular is here. So to get this angle, it's kind of ugly. However, it's pretty easy to get the angle between two vectors numerically if you code it. And so coding angular momentum should be fairly easy to do. And so if you want, maybe when we get closer to the break, we'll do a quick example where we code this and look at the arrows. And that's something that I thought we could just do on the fly and make sure I don't screw it up. So we'll look at that later. Before we get there, though, what if we had something like this book? Oh, let me check the chat here. Oh, okay. Sorry about that, Mark. I'm slow on chat. All right, so take a look at this, people. This book, I could take this and I could rotate the book about this pivot point. So I could, put a pivot on here and swing this thing around. Now, if you think about this, you could take this book. Let's say we start it right here. This is supposed to be the book. There's a pivot point right here. And now, if you think about it, we could split this up using a loop in the Python code and make, oh my gosh, chunks of the book at each different spot. You know what I'm talking about? Oh, okay, this is going to take forever. Let me just do it. Good enough. All right. And what you could do is you could say, look, I could go from this one to the ith mass, and I could see where this one's moving. If it's rotating this way, right? The velocity is going to be this way, and I think I color coded it wrong. And then you could get all the contributions of each one of these things and add them all up and get the total angular momentum. It turns out we don't need to do that, though. We have already figured out a system for doing this if we use the moment of inertia. Yeah, the moment of inertia takes into account the entire body's rotational mass, and you could take the rotational rate omega about this pivot, and this is a different way to get the moment of inertia for objects which are not a point mass. If they are extended objects like books or cylinders or disks or things we might see in the real world. So this works great for things in the real world. All right. Now, obviously, we want to be a little bit careful here. Strictly speaking, angular momentum is a vector. What direction is this angular momentum based off the picture I've shown? Usually we assume this is I hat and J hat unless otherwise specified. Which way is K hat then?
Positive.
Out of the page. And so what is the unit vector I should put on this one? What direction is it?
K hat?
Positive K hat. Yeah, and I think that's what Alonzo was going for too, right?
Yeah.
Yeah, right. So positive K hat. This one is going, whoops, it's going this way. So notice my thumb's pointing out of the page as it rotates. All right. All right. Now, let's go to a screen share of this and see if there's something I'm forgetting. All right. So, okay, in general, angular momentum is conserved if there's no external torque. This is very similar to momentum or linear momentum, just P was conserved if there was no external force, right? It's very similar to this derivation here, right? Linear momentum was conserved with no external force. Now, this is the generic definition for a point mass. These are the ways you can actually get that in practice right here. This shows you some tricks. Notice, let me scroll down a bit. Whoa, too far. Okay, this is page 83 that we're looking at, page 83. This is what I was trying to say. This is no longer called the lever arm. It's now called the impact parameter. So it gives basically the distance perpendicular to the line of motion. That red line is now the line of motion. So you might want to label that here, line of motion, not line of action. Notice here's a different way we could have done that same problem. Just like in the last chapter, we talked about R perpendicular versus F. Now we're doing R perpendicular versus V, but we could have done V perpendicular versus R. And that would get the same result. And you could see some geometry there, and it works out the same way. All right. And then again, this was the trick I mentioned we would typically use for a book or a cylinder or a disc or a thin ring or something like that. Special note regarding point masses. If you looked at I omega for a point mass, you'd get mr squared times omega. Well, since V equals R omega, one of these R's you could group with the, right? Basically, one of these R's you could group with the omega and replace it with a V. So just letting you know that this works. You could even do point masses with this formula here if you wanted to. You could even do point masses with this formula here. That's what that is all about. Next. Okay. If you have a net external torque, the angular momentum changes. That is a fact. If you don't have that external torque, if there's no net external torque, L initial will equal L final. And that brings us to the two practical ways we're going to apply this today. 1 and 2. If you have a collision where two objects hit and there's some rotation involved, you could do this type of problem. The initial angular momentum equals the final angular momentum. However, keep in mind, you have to think about the plus or minus signs on all of these because technically it's a vector, right? There's usually an implied k-hat on all terms. So again, this is just like chapter 9, where we said mass times V1 initial plus mass times V, etc. And these things, the velocities, they were not speeds. You had to remember to enter plus or minus signs on them. Same thing with the omegas. Got it? Whew. This one over here is a little bit different. This is kind of like the zombie in a canoe problem a little bit, where here you have a rotating object that changes shape. And we'll handle that in a little bit. But maybe let's focus on some of these basics first. We'll focus on the first one. We'll do all this today. Finally, at some point today, we'll try and look at this when we code. And this will show you basically the Euler-Kromer method for angular quantities and rotation. And that's the subject of lab this week. So strictly speaking, I would have to put this in here to be correct. strictly speaking, we are going to restrict ourselves to rotations in a single plane. If you've got your book there, underline that single plane. So basically about one axis. You could double underline that. All right. So we are treating these things as vectors because we are restricting the rotations to a single axis. All right. Let's do it. Let's look at 11.1. And at any time, ask any questions you want. Anybody have any questions? Just throw it in the chat or speak up. Okay. Gonna get a drink of coffee here. Okay. I'm gonna try and sketch this out and then we'll talk about it. Okay. So here's what this looks like. And I know you could go through the solutions if I'm too slow, but let's just kind of do it together, this first one, just to kind of get used to we're going to be very strict on this first one and then start using more and more shortcuts as we go on. So for part A, it says, get the angular momentum about point A. And I believe we're told that this radius here is capital R. So you got a particle going in circular motion here. L, by definition, is R cross P. Well, what is R for if we use point A? What vector is that?
2r I hat.
Mm-hmm. It's twice the radius in the I hat. That's exactly right. And then I'm going to cross that with, what's the momentum? Assume this particle has some mass m, okay? What would the momentum be?
Would it be m times v?
What direction?
J hat.
J hat, right? And so that's what I was trying to look for. I'm sweating here. I'm going to open this door. Hold on a sec. Gets really hot in this room in the afternoon right at this time, so I'm sweating here. All right, and the point I wanted to stress here was that we technically have to use vectors here, and that's what I was showing you. Notice here, we're going to get, when we do this, what do I get for the final result?
2 MVR K hat.
K hat, because I goes to J goes to K. A wheel of pain. Okay. So now what if I did this same calculation about point B? Would the radius vector be different? I'm going to color code this last one. What would I get when I do this with part B, about point B?
Is the radius just R?
Yeah, so we get MVR K hat, right? So far, so good. Now, I want to point two things out. One, you could pick any point you want. Okay, this is the angular momentum about point A. The point A you could pick this spot right here, or this spot. Now we're going to discover in the next part, some choices are better than others. Now, if we choose point A, there's nothing wrong with doing that. However, angular momentum may not be conserved about this point because there may be a torque about this point. Whereas angular momentum about B, we will discover is conserved if we do a different point. For example, what if I pick this other spot up here and have the satellite moving this way with speed V and mass M? Right? If I do it about this point, notice this vector becomes R in the I hat plus R in the J hat. You get a totally different R vector. Do you agree the momentum from the angular momentum in part A would be different? It's a different radius. It's different amounts of I's, and it's just going to be different. However, if we did this for part B, the R vector changes to R in the J hat. However, we still get the same cross product because J hat cross negative I hat still gives K hat. So what we see is the angular momentum about A will be different for every single point on the circle. However, the angular momentum, if we choose point B, is exactly the same for every point on the circle. Let me show you in a solution. Oh, go ahead.
So does that mean there's some instances where it's more convenient to use the center of mass for this?
Well, let me put it like this. I wouldn't necessarily call it the center of mass. I'd say the obvious pivot point. So let me put it this way. How about this is the shortest way? Anytime you could choose it so that the net external torque is 0, it's constant. And that's the wise choice. Now, right? Now think about what that means. Let me draw this here, just so we have all these words on the same spot as this. This is supposed to be a circle. But imagine this is like the sun or something, and there's this, or the earth and the moon, right? What direction is the force on the moon when the moon is at the top of the circle? Straight towards the center. Notice, does the line of action go through the pivot if the pivot point is point B?
Yes.
That's the trick. If there is a spot where the force goes through the pivot point, that's the obvious pivot point to choose for an angular momentum problem. Now, to be honest, this is usually pretty obvious in other problems. I just wanted to show you the math is consistent, albeit, you get different answers, but that's okay, because if you choose different points, you might get different answers. However, from a practical standpoint, like look at these two problems. Where would you guess I would put the pivot on question 11.12, Gonzalo?
11. You said 11.
Sorry,
11.2.
Right? Excuse me. On 11.2, where do you think I would put the pivot point for an angular momentum problem?
At the very top of D.
Yeah, at the pivot point. So usually, if there's a pivot point drawn, you don't need to think about this. And that's most of the problems we do. However, like Gonzalo said, he mentioned something about the center of mass, right? Give me a second. Look at 11.9 on page 88. In this case, this is in deep space. When something's flying through space and rotating, about which point does it rotate? Do you know?
Center of mass.
It's center of mass. So in this case, the pivot point would be the center of mass. So Gonzalo, that might have been what you were talking about. And I don't know if that's what you meant. So in this problem where there's no obvious pivot point and something's flying around in space, I would do exactly what you said and do torques about the center of mass. Is that, or sorry, angular momentum about the center of mass. Gonzalo, does that sort of address your question?
It does. I was just trying to relate to what we've been learning to like this. That's where the idea came from.
Yep. So yes, we will get there, but it's going to take a few problems. Is that cool?
Yeah.
Right on. Good question. All right. So let's go back to here. All right. Basically, in general, you could choose any pivot point you want. Try to pick an easy one, like the obvious pivot in a problem, or the center of a circular orbit if something's doing a circular orbit. All right. Those are the two obvious choices for doing angular momentum. All right. Now, next, let's look at 11.2 and see if we can get this term impact parameter down so we can learn some of the shortcuts. Okay, I'm going to draw this one up. Give me a second. You can read it and try and work it out. Okay, so we already know this one. The best choice. Oh man, that's psychedelic with all these doors over here. For some reason, that's like tripping me out. I'm gonna just scoot this way a little bit. What doors? I live in a box. All right, so I'm not used to having that door open. Kids are not here right now, so that's cool. In this case, I think it's pretty obvious we want to choose the pivot as the pivot point. Got it. That's part A. Part B, I believe, asks us to find the impact parameter. Is that right? Just getting my paper book out. Yes, impact parameter. So remember, impact parameter is R perp. What is that in this particular problem? Is it X? Is it D? Is it something else? What do you think?
Would it be the rod, the D?
Yes. So to help everybody understand it, in case you don't know how to get that, the first thing you draw is the, what am I drawing here?
Line of motion.
Yes, the line of motion. And then you draw a line from, well, let me be clear. This is the R vector, but R perpendicular is this. It forms that perpendicular bisector. Now I offset it a little bit just so I could see it. So this right here is R perpendicular. Okay. And let me check the chat in case I missed something here. Got it. You're on it, Juan. Okay. So got it. Now let's get the angular momentum really fast. I want to use the equation MVR perpendicular, right? However, we got to be a little bit careful. These are the same kinds of tricks I might do to you on a test day, so let's pay attention. If I'm trying to get the angular momentum, what mass should I use here?
The mass of the rod?
The mass of the particle that's moving in the rotation, right? So imagine if I looked at this, whoops, hold on, going mobile. There's that mass right there, that blue one. That's what's essentially rotating here. The rod is just hanging there doing nothing. Alonzo, does that make sense why I'm saying that?
Yeah.
Okay. So I need to use m/2 in this case because the mass of the particle that's actually rotating was said to be m/2 in the problem. Oh, that's sneaky Jarstead. And then in this case, R perpendicular is D. What did I forget to write down?
Unit vector.
Unit vector. Which direction applies? Line up your fingers with the R vector. Curl
Out
them
of the
in-
page.
Out of the page, which is what?
Positive K. Yeah.
Positive K hat. So we get a positive K hat here. That's a little bit faster than doing the wheel of pain every single time. You can't always use this trick, but when you can, it's so much nicer you should. That's the angular momentum in this problem. Piece of cake, right? What could go wrong? Probably the next problem. Here it comes, people. Easy, easy, super hard. Here we go. I'm going to look at this one. Yep, that's how it goes, right? Now, I just want to point this out. Let's look at this problem and see this is finally going to be a realistic problem rather than just learning the math. You have a rod of mass M, it's length D, it's hanging from a frictionless pivot. Notice that I've started using D for the lengths instead of L, because L in this chapter is angular momentum. So if you have an old version of the book, the workbook, you may see some L's. Just change any of the lengths to D's and you should be good. I think I changed the entire book, but if I missed one, I apologize. So in this chapter, length is going to be D. It's shot from a gun with a large unknown speed, V. So V is unknown, even though it's given because I specifically state that. V is so large that you can think of it as straight line motion. Obviously, in the real world, this is going to fall below it. But what I'm saying is it's going so fast that it falls below it by such a negligible amount, we're going to completely ignore it. Okay. It sticks to the center of the rod. And afterwards, this thing is going to swing up in the air. Afterwards, it swings up parallel to the ceiling. So let's see if I can get this over here now. Whoops. Let's try 250. There we go. So it's going to swing up afterwards until it's basically level to the ground, but not hit the ceiling. So afterwards, the rod is going to swing up to there. The lump of clay is still going to be stuck to the center. Figure not to scale. Woof. Now, in this case, we need to determine the impact parameter. What do you think that is for this problem? Does anybody feel brave and want to try drawing on my screen? I'm going to wait you out. Who's willing to give it a shot? It's okay to be wrong. And maybe I'll help you out a little bit. What's the first thing I did last time when trying to figure out the impact parameter? What was the first thing I drew?
Line of motion.
Line of motion. So I'll do that part. So now what do I need to do to get the impact parameter?
R.
Yeah, where should that be? Do you want to take a shot at it or do you want somebody else to do it? What do you feel like? You want to try it, Alonzo?
Yeah.
Okay, see if you could draw right on my screen and I'll tell you if you got it right or wrong. Pretty close, pretty close. So that's supposed to be a right angle, right? So I would say it's probably a little bit closer to that, but that's basically right on what you draw. So a right angle, so that's the perpendicular bisector. Nice job. So then the question becomes, what is that distance? If we could figure that out, we know the angular momentum for this particle about this system, because sometimes things aren't always at right angles. Any ideas here?
Wouldn't that rule still apply? The one that you said earlier, the radius from the pivot point?
Yes, you could do it this way. Is that what you're saying? You could go this way. R vector, and then this is phi. But the problem is we don't know R or phi. It would be kind of a mess to figure it out, right? I guess we could figure out R, actually. We know R pretty easily. Agreed? It's just negative D in the J hat plus negative I in the I hat. Do you agree with that for R vector? But we don't know this angle. So trying to figure out that is a little bit tricky. So what he was saying is that R perpendicular, I think this is what he was saying, was R times sine of phi, right?
Yeah.
And that would work, but we don't know phi. So you could try and do some math to figure out phi, and that could be done. In practice, this is something that we're going to see all the time. You got to do a lot of geometry. So I'm going to make this a little bigger. Let me see if all this can fit on a single page there. Take a look at this. I'm going to pause and see if you could follow that. Oh, go ahead.
Okay, I get it. So like we could use, like what you mean by geometry, we could use those angles like to relate like the 90 minus
Yes.
phi to the other side.
Absolutely. For example, this one, I'm going to call this double line is equal to that line by whatever you call that in geometry, vertex angles or something, right?
Yeah, I forgot what it's called too, but I know what it
Yeah,
is.
yeah, exactly. I don't care about the names of stuff. I should, but whatever. If this is a right triangle, how could I figure out this is 90? Well, I know the angles in a triangle add to 180. So if I called this alpha, beta, and gamma, fish swimming down, I know that alpha plus beta plus gamma, the three angles that make up a triangle, always sum to 180. And so we're using that geometry rule too, essentially, right? That's how we get the 90 minus phi to get the ball rolling. Well, once this is 90 minus phi, you could use this rule again to say, well, the upper angle has to be phi because 180 degrees has to equal 90 degrees plus 90 minus phi plus this mystery angle. I'll call it psi just because I'm running out of things. So if this angle was psi, well, when you do the math, the two 90s drop out, the phi moves over. We find out that psi is equal to phi. So that's what I mean by doing some geometry. Out of there, after all that, notice that R perpendicular is this junk. And if anybody in the class said, oh, I could tell it was going to be D over root 5 just by looking at it, I encourage you to teach the class instead of me. Okay. So this was not something that I thought was obvious right away. If you saw that, you're doing great. Something that you might not be familiar with is looking at this. Rather than figure out the angles directly, I figured out the cosine of the angle. Now think about that. Rather than figuring out the angle directly, rather than solving for phi, you could figure out sine of phi and cosine of phi from the picture. Who uses this all the time? Civil engineers, people building objects. So we will use it all the time. Got it, Alan? We will use these tricks all the time in the next chapter. So geometry is hugely important. These kind of geometry tricks and this trick of using cosine of an angle instead of solving for the angle or using sine of an angle. We are going to use that a lot on the next two chapters in the final, just letting you know. So out of all this, we could get the angular momentum. All right. Let's go back to here and see what's next. All right. So in theory, we could do that. And I'm going to pause and see if there's any questions on parts A and B. All right. Now, Next, what is the moment of inertia of the rod and clay system after the collision? After the collision. Well, let's just go look at that. The total moment of inertia is going to be the moment of inertia of the rod plus the moment of inertia of the clay. Let me get my better annotation out here. The rod is going to be a 1/3 ml squared, but now we're using L for angular momentum, so we're using D for the length of the rod. The clay is basically a point mass. There's the mass of the point mass. Notice it's m/2. And the distance, because it hits right here in the center, the clay is going to be right at the center. The distance from the pivot point is d/2. And I should have used a decimal here. My bad. Next, before we go on to the next part, let me show you the question. It says, what is the rotation rate of the rod just after the collision? Ding, 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 ding. An alarm is going off in my brain. We're talking about a collision and rotation, angular momentum. Again, I see the words collision with rotation. I think about angular momentum. That's what angular momentum is good at. Now let's go look at the solution. Take a look at it. L initial equals L final. I'm assuming a k-hat on everything, right? We're going to ignore the k-hat just because they drop out after the first line anyways. MVD, that's the moment of inertia initial from the point mass, swinging in to hit it. Afterwards, I need the total moment of inertia and its rotation rate. After flipping all this junk around, you get this junk, you get this junk, you get this junk. I should have used a decimal. Sorry, my bad. All right, that's cool. That's a practical application of this. You could find out the rotation rate after impact. Keep in mind now, V is an unknown. Ultimately, we're going to solve for V in a minute. Okay, let's go back to the question. Part E, what assumption did I make? If I want to use conservation of angular momentum, what is the assumption we have to make?
No net external torque.
Beautiful. Let's look at this picture and see if that seems true. So we shouldn't blindly use angular momentum. We should understand why it's acceptable to use it. Somebody, anybody, give me one force on the rod during the collision. And actually, let's do this on the whiteboard. During the collision, here's the rod. Give me one force acting on it. Here's the ball smushing into it. What's one force act? Oh, I see there's something in the chat there. Normal. I don't know what you mean by normal. It's not being supported by a surface, right? Usually we associated normal force with a surface. Go ahead, Alonzo.
The point mass, the force going to the right
Yeah, well, it's actually going this way, right?
or diagonally. Would it go diagonally because the rod can only go swing?
Oh, so you're noticing that the rod is restricted in its motion. The rod can't go up in that way. So tell me, is the rod being acted on by something else? Let's come back to your question. What other forces act on this? Alonzo, try another one.
The rod going down, mg.
Yeah, that's going to be right at the center. What
And then
else?
At the pivot point, it's resisting.
Both up and to the left to keep it from flying that way. Does that address your question?
Yeah.
So there's going to be an Rx and an Ry. Basically, there's some reaction force off this way. And that's going to offset some of that clay, but not. Now, here's the other thing. What are the forces on the clay? So I'm going to forget that clay is drawn right there. All right. What are the forces on the clay now?
The force of the rod.
That's right. In which way is that going to point?
The opposite of the force of the clay.
Mm-hmm. What else? That's what's happening, right? The clay pushes the rod that way because it's moving that way. The rod says, hey, Newton's third law is valid. Pushes backwards. Now, which of these forces are internal to the rod clay system?
The force acting on the rod and the force acting on the clay.
Those are internal. So I don't have to worry about those forces when I'm worried about, does this have an external torque? Let's look at these. Does mg cause a torque about the pivot point?
It doesn't because it goes through the point.
Line of action through the pivot. And same for these two. So there's no external torque. So what we see is the sum of external torques equals 0. Now, wait a minute. What if this rod swings up a little bit? As it swings up, these two will never cause a torque. What about mg? If you're up here, does mg cause a torque? If the rod was at this angle, would gravity cause a torque on the rod?
It would in the y component.
It
or the
would.
j
It would cause it. It would. However, if the collision happens quickly, it's approximately equal to 0. So as long as the collision happens before it swings up that far, this is a valid assumption. Is that good? Now, I want to point out are the external forces negligible? Is this true? Is the sum of external forces approximately equal to 0? What does your guess say? What do you think? It's okay to be wrong. Just take a guess.
No.
No, this one is not balanced. Look at that. So here's the deal. This pivot point doesn't cause a torque. And so as a result, we could totally do this problem with angular momentum. However, the pivot point does cause a significant force, as alluded to by Alonso at the very beginning. So we know that we can't do this problem with momentum. Basically, P initial is not equal to P final. However, L initial is equal to L final. Got it? That's what we kind of want to know about these. All right. That's a lot to take in. Finally, let's get back to here. That was the assumptions I made to use conservation of angular momentum. How much does the center of mass of the rod rise after the collision? The rod goes there. I got a point mass sitting at the middle. How much did the center of mass rise?
It didn't.
This is where it was just right during the collision, right? What's that distance right there?
D over 2.
D over 2. Does that make sense why the center of mass actually went up? Again, okay, so be careful here. We've got to be careful. There's, let me see these words. Where are they?
But the center of mass of the rod didn't change, just like the position, right?
That's right. The center of mass of the rod is still at the middle of it, but after it rotates up, so it's going to hit, it's going to stick, it's going to be rotating with some rate omega. And then when it gets to the top, omega final is going to equal 0. It's going to come to the top and swing up here. Okay. So in this case, notice, what is our final goal here? To figure out the initial speed. How do we do that? Check this out. We do a conservation of angular momentum problem to get a relationship between omega, which is unknown, and v, which is unknown. Next, we do an energy problem using the center of mass position as the height. So that's where this d over 2 comes from here. Okay, so if you look at this one, there's a rod here. It's going here. It's got some rate omega. And I got to set this level as height equals 0. And I'll check the chat in just a second. Then when it gets to the top, we've got this rod here. There's this center mass. The height final is d over 2. And I promise I'll get to the chat in just a second. But omega final is equal to 0. That's what I did right here. Yep, ouch is correct. That's a pretty succinct summary of this chapter. Ouch. However, it should be straightforward if you did all the work in chapter whatever that was, 10. Now, side note, I just had a student come to me during my office hours that had me for class, and they struggled with the class, and they didn't pass the first time, and they had to retake it, and they had to grind like crazy. They came back today and they showed me a letter from UCSD saying they got accepted for an internship. And the guy said that during the interview, the people kept asking him about stuff. And he kept saying, well, I did this in my physics class. Well, I did this in my physics class. And they were impressed and they hired him. So yes, it's a lot of BS. Yes, you're working hard. Yes, you don't want to do it. And yes, this feels like it doesn't matter. However, based on one anecdotal point of evidence, this helps you get a job. And actually, I have many anecdotal points of evidence that indicate this stuff will help you. So when you're hurting and you're bored and you want to quit, this is the kind of stuff that helps you get a job. And specifically, all the bullshit I ask you to do in lab will help you on your resume eventually. So it's going to help out. Hang in there and fight. You can do this. Fight for your grade, all right? You can do it. Don't give up. We got, like, what, 5 weeks to go. Manufacture some motivation somehow, some way, and make this happen. All right, back to the problem. A bunch of BS. You get an answer. You work through it. I should have used a decimal. Woo! Okay, that's a test level question. If anything, that's maybe even slightly harder than the average test question. All right. Wowza. Let me see where we're at now. All right. I think, actually, let's go to this one. Sorry. It's almost time for a break, so let me just confirm. Looking at this big picture, this thing is basically a ballistic pendulum. We have some stuff we know, some stuff we don't know. We find out we have to use center of mass. We have to use angular momentum. We have to use moment of inertia. We had to use conservation of energy. Woof, woof, woof. This gets complicated. However, that's about as hard as this stuff gets in this chapter. That's probably one of the hardest problems in this entire chapter. So cool. Now, before we take the break, I'll mention this problem. This is probably a good exercise for home. I was trying to imagine a problem that you could use to code up a pulley problem. And so when you look at this one, you could do FBDs and torques to get the angular acceleration. In this case, because there's a torque, there's a change in angular momentum. And if you wanted to code this up, here is the procedure to make the code to make this simulation. You could calculate the net torque based on current angular position, et cetera, et cetera, et cetera, and go through this. If you want, you're going to do this in lab on Thursday, maybe not for this specific problem, but for another one. And then finally, let me give you another example. We just did a problem with two objects rotating with a collision, right? Actually, let's take our break now. All right, screw it. Let's take our break, and then we're going to pick up here on page 86 because I want to do page 86 as a whole. So this is as good a time as any. So my clock says 5:40, so we'll start back up at 5:50. I'll try and make that simulation really quick so we can visualize this. Any questions before we go on break? Any questions? You could do this stuff. You could totally do it. right, I think that's when we said we would come back, or approximately. So as a fun way to come back from the break, I'm showing you a code that I just started writing here. So I literally started this, I got a drink and then came back and started coding this up. So let's see if this makes sense to you. All right. This stuff here is pretty boring. That's just draw the coordinate axes. Now you'll notice I'm kind of phrasing this in a slightly different way. I don't know if you're used to this, but basically I declare the object is a cylinder, and then afterwards, line by line, I modify the attributes. I don't know why. I just kind of like that right now. It just makes it easier for me to go through this list rather than having to read sideways and pick something out. Obviously, here's a label where I didn't obey that convention, but whatever. Now, here's where we start to get into the meat of the code. I'm going to draw a ball, and that's going to be a sphere. I'm going to set the color to this nice cyan color, 1 part green, 1 part blue. I'm going to define an attribute known as its velocity. I'm going to say it's moving in the x-axis. And actually, maybe I'll give it a position here. Let's say it's -5 in the x, and how about +3 in the j hat and 0 in the k hat. All right, so I'm just giving it some random position vector. This is the starting. So these are the initial properties of a ball. Next, I'm going to draw a velocity arrow. The arrow's position will be the tail of it, right? The tail of the arrow is the arrow's position, so that's at the ball's position. The axis is going to correspond to the ball's velocity vector. So that's okay, right? Axis has to be a vector. Well, ball's velocity is a vector. And then the color, I'm just going to make it the same as the balls. Next, I'm going to draw a pivot point. And so here I decided to make the pivot red, draw it a little bit smaller. So notice the default radius up here, if you care, is 1, the default radius. So if you wanted to, we could actually specify that. Let's make it 0.5 or something, right? So just so it's all explicitly stated. So notice the pivot point, I didn't specify a position. The default position is the origin, but we could change that later if we wanted to. Or we could change it right now, right? We could just say pivot dot position. We could put the pivot wherever we want. It's going to be a vector. And let's say it's 3 in the I hat, -1 in the J hat. And let's keep things simple for now and keep the K hat out of it. All right. Next, I'm going to draw an R arrow. So that's an arrow. The position is going to be the tail of it starts at the pivot. And I go from the pivot to the location of the velocity. So that's this direction. And here I'm making this a green arrow. Now the angular momentum, I was just about to type that in. What do I need to do to finish this out? So the angular momentum is defined as what physics equation? Do you remember?
Yeah, it should be omega is equal to 2 pi over big T is equal to 2 pi f.
Oh, no, that's for angular speed. I want angular momentum. You were thinking omega is 2 pi over the period, which is correct. But that is not what I was asking about. What is this thing? L. Cross
R.
what?
P.
Yes, P. So now how do I get that from the ball? What do I type next? Do you remember?
The mass times the velocity, or m.
Yeah, what should I type? So what did I say the mass was, do you think?
Ball dot m times.
Yeah, you're on it.
W.
All right. That's going to compute it. So now, if we want to draw an arrow associated with it, right, that should be how about we just leave it white? We need to put it somewhere. Where is the logical spot to put the angular momentum's tail? Or where should I put the position of this arrow? At the pivot, because it's angular momentum about that pivot. The angular momentum vector is represented by an arrow on the axis of rotation. So now that will draw the arrow. And now if I just go down to here and comment this out, let me comment this out, and we run this. Hopefully this runs, and I just literally haven't run it yet. All right, so now in this case, we can kind of see what's going on here. I didn't label these very well, but this is the R vector. This up here is the velocity vector. And notice the angular momentum, L vector, points into the page. Try that with the right-hand rule. Just stick your hand up to the monitor and kind of look at it. See how your thumb goes into the page? And so, again, if you see this thing, we could swivel it and you get a feeling for it. All right. Oh my gosh, I'm having some trouble here. There we go. Oh my gosh, it's clicking on me. But hopefully that gives you a feeling for it. Now, what I was hoping to do is to animate this so that you could actually see it. So that's what this is doing. And I don't want to waste all day on this, but what you'd have to do here is first you update the ball's position using this equation, right? This equation right here is essentially saying, oh, whoops, I'm on white. Let me get a different color. This equation is essentially saying x final equals x initial plus v initial t plus 1/2 at squared, except in this particular problem, a is equal to 0. So that's all I'm doing right there. That's what this equation is. After you know that, we could go through and literally recompute all of these things up in there again. So we could say, well, we could do this. In this case, actually, the velocity is not going to change. So I don't think anything is going to update with the angular momentum, right? However, we would say V, the arrow's position should have to equal the ball's new position, right? And we're going to have to calculate a new value of R. So R arrow dot axis would have to be recomputed. Well, I'm just going to copy what I wrote up here. Now this one, whoops. So that's just recomputing the new R arrow based on the new position as it travels. And then notice the tail is staying fixed to the pivot, so I don't need to update that. However, this is going to change. So let's stick that inside the loop, right? Because this is now different because the ball's position changed. However, we should find, let's see. The axis should remain unchanged if the code is working correctly. And then we'll increment the time. Now let's see, I did this really quickly. Hopefully this makes sense. And if this is the part that I haven't done in class before, I hope this is helping some of you. So that's what's going on as this thing moves. I don't know if that was educational or not, but any questions on that? That's how you could simulate these types of things.
I have a question.
Yes.
But it's probably like later on in the chapter, but say if it the green arrow, the R arrow, was attached to a string or a rod, and then the blue was moving in a circular direction, the wouldn't change.
So how could we do this? So what we could do is we could do something like this. Let me define this up here first. Just, I don't know. I can't help it. It's a good habit. Let's just say let's start with 0, 0, 0. And then what we'll do here. Yeah. Now what I'm going to do here is I'm going to go into here and say, let's say this is equal to, let's see, it's going to be a vector. And let's say it's negative, I'm going to hard code it. Okay. -9 times, oh shoot. You know what? This is going to be it's going to take me longer than just being able to flip it up. But if we did this thing where it was moving in a circle, I tell you what I could show you here. If we go like this, it would look a little bit like this, except what I'm showing you here is the force and the angular momentum. So now what would happen here, I don't know, I'd have to pause this at some point, so I'd have to put in a weight. But the idea here is the green vector is the R vector as this thing's orbit. And this is what you are doing in lab this week. You're going to try and make something oscillate like this as it swings back and forth. So in this case, when it's rotating this way, the angular momentum would be out of the page. When it's rotating that way, the angular momentum would be into the page. Hopefully I got that right. Did I do that right? Yes. Sorry, that's supposed to be an X. Right? And the size of the arrow would depend on the speed. So, Alonzo, I know this isn't exactly what you asked, but it would be something like this, where you could have forces that are causing this thing to go in a circle. And if you gave this thing some initial velocity, you could actually make this thing rotate in a circle and it would do that. Is that good for you?
Yeah. So in this problem, it's kind of what is it called? The isolating, or like going side to side.
Yeah, and all I'm doing here is torque and constant acceleration kinematics. So this is actually going back a bit. This is not constant angular momentum because there's an external torque associated with mg. So in this problem, you could do, so let me see if I do this here. Where did I do? Okay, omega. I'm looking for omega. Well, let's just try this where we give it a, let me think. Let's see if this works. Oh, I reset it somewhere. So I'm not able to give it an initial angular momentum. Sorry. All right. But I feel like I'm getting pretty far off topic here, Alonzo. Did I answer your question or not?
Yeah.
All right. Good enough. All right. So we'll explore this more in lab. That's your kind of foreshadowing on that. My apologies if I took too long on that digression. But hopefully that will, oh, whoops. Let's get to the workbook now. All right. So again, we could use this angular momentum technique for problems where there's no external torque. So look at this one. I have two objects that hit, they collide, there's rotation. This seems like a good way to go. It's actually, I'm going to leave this one for you to do at home. It's pretty straightforward, but you should do it. There's a lot of good nuggets in there. So interestingly enough, this is a simple model of a clutch on a vehicle. Right. And so you have two plates, one of them's initially spinning and one of them is not. And then you could talk about, oh, friction causes the two to come to the same rotation rate. That's very similar to a clutch. Now, what I would like to focus on next is this other type of problem that we haven't done yet. A rotating object that changes shape. Now, the classic example would be a figure skater. You're spinning around with your arms out or in. This is not going to work too well with headphones, but yeah. So obviously, if you bring your arms out or in, you change your shape. Yep. All right. And so, but let's look at another example. Whoops, I forgot to hit share screen. Oh, wait, wrong button. I can get there. I can do this. I can share a screen. There we go. Hey, here we go. Look at this neutron star. I'm not a huge astro fan, but I do think this is amazingly cool. The numbers in here are somewhat realistic as well, as crazy as you're going to find out they are. Imagine you have a star and it's initially rotating with a period of 30 days. And this goes to what Gonzalo was saying earlier. The period relates to the thing omega. Gonzalo, what was that relationship? Do you remember?
Yeah, so it was omega is equal to 2 pi over big T,
Yeah,
which is equal to 2 pi f.
right. So we're going to use that all the time. We're going to use it again in a couple of chapters and again next semester. So just kind of memorize this relationship right here. We just use it so often. It pops up every couple of chapters. All right. All right. So let's take a look at this one. We have the star that starts out at this huge radius. Now think about that, 10 to the 4th kilometers, and it's going to shrink down to 3 kilometers. Smaller than Allen Hancock College, maybe approximately the same size as Allen Hancock College, the entire campus. Okay, maybe not quite, but close to that. So, but 3 kilometers is pretty small for a star. But this is not implausible. This kind of thing could, in theory, happen. All right. So we know this equation. So Gonzalo did part A for us. All right. So next, write an expression for angular momentum using period instead of angular velocity. Well, that's not too bad. I'm just going to go to the solutions because I think you guys could follow this pretty straightforward. What problem was this? 11.6. Take a look at that equation. See if you follow that. I just replace the omegas with 2 pi over the periods. The 2 pi's drop, and I get this final result. Piece of cake. Now I'm going to rearrange that and solve it for the final period because I want to analyze the final period of this star. Remember, it's changing. The mass of the star isn't changing. I'm assuming this is the moment of inertia of what shape?
A disk?
Sphere. Star is like a sphere. Disk is 1/2. Solid sphere is 2/5. This might not be exactly right, but so what? Gets the idea across. So now if I know, oh, the 2/5 are going to drop out, the mass is going to drop out. I have this final radius and this initial radius squared. The final period is 0.23 seconds, a quarter of a second. Instead of taking 30 days to rotate, this star is going to speed up and rotate 4 times every second. That is insane. And this is something that's hard to appreciate until you do astronomical problems. The numbers involved can seem bafflingly large, and then at the same time, you can get these crazy small results. There are some amazing results. So I'm not a huge astro fan, but I can appreciate it from that standpoint. The scale of objects there is just, yeah, it's amazing. You just get tremendous scales. All right, so what are we doing here? Just to be clear, I figured out the new period using conservation of angular momentum. Now, I could also get the fractional change in energy. Let's take a look at that. Well, that's just E final minus E initial over E initial. Whoops. The 1/2s are all going to drop out. And here is the step that's kind of, you got to know and have some experience. Because I know I initial omega initial equals I final omega final. If that is true, I could actually rearrange this and say, well, isn't omega final just I initial over I final times omega initial. Again, this all comes from angular momentum being conserved. L initial equals L final as long as no external torque. So this is the step. I take this junk right here and I plug it in right there. Give me a sec. That's what I did. And why? Why is this trick used? Well, now look at all the omega initials drop out. And we get this much simpler result. Now check this change in energy out. 11 million times more energy. Holy schnookums. Waka flocka. That's a lot of energy change. Holy cow. All right. So I love it. -1. That doesn't matter at all when you're talking about 11 million. But this star gains so much energy. Where does all that energy come from?
This might be a stretch, but I personally
Yeah.
think it's because of energy mass equivalence. You know, E equals mc squared.
I don't think you need that at all. That's a good guess. Good guess.
Because it shrunk, it got smaller. So
Okay. How does that change the energy?
Would the mass be converted into energy? The loss of mass?
So the way I see it is, think about this object. This is not to scale, but all of this mass out here on the edge is raised up by 10 to the 4th kilometers, basically. And it falls down into the center, and you get a massive reduction from gravitational energy being converted. The planet's own gravity causes the star to collapse in on itself and causes all of this mass to reduce its height. Now, we haven't talked about chapter 13, and it's very complicated. In theory, you could do conservation of energy here, except do you know how to do the gravitational potential energy associated with every single point in a star? I don't have that like right here at my fingertips right now. After chapter 13, we might. But right now, we don't know how to calculate that gravitational potential energy. So if I could cheat and go to the solution, gravity is causing this star to collapse on itself. Think about it. The star has an outwards radiation pressure that's keeping it going from that E equals mc squared that you were talking about, right? That's the fusion in the star that keeps this thing boiling and growing. However, you're going to have gravity pulling it in, and eventually gravity is going to cause this star to collapse in on itself. So that's kind of interesting. Great. All right. Man, it's been a long day. I'm kind of faded already. Let's go to this one. Let me go to 100. All right. Look at class, 11.7, the class volunteer. They hold some masses out. Oh, geez. Sorry. Man, I feel like I'm sloppy clicking today. I just can't seem to click on the right button today. Okay. Look at 11.7 here. Sorry, I shrunk it down and I have to sneeze. Sorry about that. Does 11.7 look more like an 11.5 style problem or an 11.6 style problem, just based off the picture? Does this picture down here look more like 11.6 or 11.5? Get in the chat. I would say not 5, Christian, because take a look.
I would say 6.
Yeah, so here I have an object that changes shape while
It's like
it's
the figure
rotating.
skater.
This is like the figure skater that's closing his arms or her arms as they skate. And so these problems right here use this second form where you have one object, you calculate its initial and its final moment of inertia, and that allows you to to get a relationship between either the periods or the rotation rates. Whereas this one up here shows two objects colliding. So there it makes sense to have I1 and I2 because they have different omegas to start. And that's the difference I wanted to point out. Christian, are you good with that? Let me check the chat. Right on, right on. So that's one of the things I wanted you to look at there. Let's go to here. Let's clear these out. All right, so let's keep scrolling down. Hey, you. Watch out. The biggest mistake students make is in chapter 10, we did rotational energy all the time. In this problem, we have seen a number of cases where energy is not conserved. So you have to be careful. The most common mistake people make is they really practice the crap out of chapter 10, and then they assume every problem is a chapter 10 problem. Well, that doesn't always work. Sometimes there are external forces or work done. So you have to be careful. You can't always use energy conservation. Moral of the story, learn to identify which problems are rotational energy problems and which problems are angular momentum. For example, in this one, let's take a look at it. Let's start with part A. And so I'll give you a second to read. You got a lump of clay, it's moving. It's got some speed V, its mass is M. This thing has mass 2m, its length is d. Collision time is very short, and it swings up to some angle. All right, there's stage 1, stage 2, and stage 3. This is at the max, right? So when is it okay to use conservation of angular momentum? What does your gut tell you?
1 and 2.
Correct. During the collision stages, just before the collision and just after. That's when you do momentum.
Is it because stage 3 has that external force?
External torque. There's always the external force, right? So during the collision, there's this force here, Rx. That's why we can't say, right? There's also Ry, and there's also mg, and at the center mass is probably about right there. And it's 3 mg because there's 2m from one and m from the other, right? So the rod has mass 2m. This has mass m. So we got to watch out. The total mass is 3 mg. But yeah, this 3 mg causes a torque. So in between stages 2 and 3, 3 mg causes a torque. Nice job. I would say you did a good job on that one. You got that? Any questions about why I said it's this stage? This doesn't work. This doesn't work. And these two don't apply. How about conservation of energy? Can you even use conservation of energy or not? And if so, when does it apply? Between which stages? I'm going to remind you, if we want E initial equal to E final, what has to be equal to 0? It's not force. It's not torque. It's what? What do we need to equal 0?
Would it have to be torque?
Nope. If torque is 0, angular momentum is conserved. If force external is 0, regular momentum is conserved.
Velocity? Or,
Work. Remember that term work? You need the work done, external and non-conservative, to equal 0. Remember we used to say E initial plus work, non-conservative and external? Remember that? So work from non-conservative things such as friction. So let me ask you, when does that apply here? Let's start with here. Between stages 1 and 2, is there going to be external or non-conservative work? What does your gut tell you? When the clay smashes into the rod and sticks to it, do you think energy is conserved? Think back to chapter 9.
Yes.
No.
Uh,
You lose energy to deform the clay. Now, strictly speaking, energy is conserved in the entire universe, but what happens here is when the clay smashes into there, try to draw that over here. When the clay smashes into there, some of the macroscopic observable velocity of the entire clay gets converted to vibration in the particles of clay itself and in the particles of wood. And then that radiates heat out to the universe.
oh, my bad. I was thinking of elastic.
Ah, if it's elastic, you'd be right. This is a perfectly inelastic. So what happens here is some of the energy gets lost into the molecules. It's not that it's not still there, it's that we can't see it and measure it, and then it gets radiated into space eventually. So it's not between 1 and 2, and it's not going to make sense between 1 and 3. So the only choice left is between or none of these. Do you think energy is conserved between stages 2 and 3?
can you see it as if it was conserved, the pendulum or the rod would keep swinging forever, but because it doesn't?
That's not true. For example, when this swings up, what kind of energy is present here?
There's potential and kinetic energy.
So it's not that it wouldn't swing up because it doesn't swing up forever. It swings up and stops because it converts all the kinetic energy into gravitational. So this is what I would say. The kinetic energy is equal to 0 in the end, but gravitational is non-zero. Whereas here, U due to gravity is equal to 0, but the kinetic is greater than 0. This actually is a conservation of energy problem between stages 2 and 3. Between stages 2 and 3, there are forces present, but the reaction forces at the pivot do no work. And furthermore, the gravitational force is expressible as a conservative force, so it's not non-conservative. Gravity is a conservative force, so it conserves energy. If we convert it to potential energy, sorry. Oh my gosh. All right. Now okay, so there's that stuff. That was the reasoning. We kind of walked through it. Why does the center of mass matter? I kind of showed you that. To be clear, the center of mass is probably about right there. That's what matters for the gravitational potential energy in this problem. We need to figure out the height that the center of mass changes. That's why the center of mass matters. And then the rest of this, let's take a quick cruise through the solution here. What is this, 11.8? There's a bunch of words where, okay, so this is kind of, oh my gosh. So there's the problem. Between stages 1 and 2, I did a conservation of angular momentum. Between stages 2 and 3, I did a conservation of energy. We have to understand why, or it gets frustrating on test day for you, right? On test day, all the questions look almost the same. So you want to know why you use a technique. Does the center of mass affect the moment of inertia? Well, take a look. I already accounted for that this way. So look what I did for the moment of inertia there. Does that make sense?
Yeah.
And so, yes, it does in a sense. However, I could handle it just the simple way. I didn't have to do the parallel axis theorem, if that's what you were wondering.
Yeah, that's what I was thinking.
Now, to be honest, you could say, well, you did use the parallel axis theorem for this, didn't I? Because to get this result, you could get this from 1/12 times 2m d squared plus the amount it's shifted, 2m times d over 2 quantity squared. So you could argue that I did use the parallel axis theorem by using the formula for the rod at its end. I used I parallel equals I rod center, which is the 1/12. Does that make sense, Gonzalo?
Yeah, I appreciate the clarification.
Let me just finish it so it's all on the screen. All right, so that's, you're good to go on that one, right?
Yeah, thank you again.
Yep, good. Okay, and so, woo, then look at this energy problem. Yowza, yowza, yowza. Oh my gosh, combining the two results on the next page, there you go. Not too bad. It gets faster if you do the practice. I'm going to show you another one. Let's look at this one. 11.9. I'm going to pause and let you read for a second. I'll get a drink of water. We're in deep space. Apologies for me putting some problems in deep space. It's just easier. If I put things in deep space, it's okay that they're just floating around and I don't have to, it just takes fewer words. There are examples of this in the real world. You could imagine this is like a hockey stick and this is a hockey puck that hits it and you're viewing it from above. The same physics would apply. However, if we put this thing in deep space, we don't have to worry about external forces. Agreed? So the reason physicists will do these problems in deep space is so that you can simplify the math and make a problem that is physically approachable. They do relate to real world problems too. All right, next. The rod has some mass and length. The point mass has some mass and speed. The clay collides with and sticks to the end of the rod. Which of these conservation laws apply, people? Just before to just after. Go ahead.
Angular momentum.
That's half credit. What else applies?
Linear momentum?
Yeah, there's no pivot in this problem. The pivot was the whole problem. Remember when we had a pivot up here and there was an Rx? I'm like, oh, blah, 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 blah. This Rx prevents causes a net external force, blah, 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 blah. Without this pivot here, there's no Rx. Linear momentum is also conserved, or regular momentum. So the correct answer here is both of them. Why is the center of mass relevant in this problem?
That's the pivot point, or that's where
That's the pivot point where it rotates. You got it. Yeah. So in this one, that's going to be the pivot point about which it rotates. So if we go into the solutions and look at this one, Okay, there's some words. Oof. So notice this one, Gonzalo, you do have to use this parallel axis theorem, right?
Oh no.
You see what I'm saying now? So this is, I think, what you were wondering about earlier, right?
Yeah, but I regret it now.
Well, hope there's a pivot point on the final or you're toast. No, but to be honest, it's not as bad as it looks. First, are you okay with the center of mass calculation that I did? What I did is I just said, let's make the bottom 0, let's make the top d/2 or the middle of this thing. And so what I did is I said, okay, let's do a quick center of mass calculation. Well, there that is. It's d/3. So what I'm saying here is this distance here is d/3. I did the math, the center of mass. Next, I said, well, this distance right up here is just d/2 minus d/3, which is just d/6. So now I know, let me do that one more time in green. I know that this distance right here is d/6. Not that bad. No one step is that bad. So when I do the parallel axis theorem, my rod has mass 2m, not m. The distance it's shifted from the center of the rod is d/6. And so this is now how you get that parallel axis bit. Does that make any kind of sense? And
Yeah.
to be honest, I would have just gone to decimals. My new style is just forget these fractions. Go straight to decimals in your calculator, people. You do not have to do all this 2/9 and stuff. However, if you feel that's instructive, go for it. You could do it either way. Either way would be full credit, decimals or fractions. Next, now for the point mass, I got to add in the point mass too, right? Well, this one has distance d/3. Its mass is m. There's how I get that. The total moment of inertia is, oh, that cracks me up. Look at that. By chance, it turns out to be 1/3 md squared. If you weren't paying attention and you just wrote down some random bullshit formula, you probably would have got that right. Oh my gosh, these are the things I find funny. Now I could do conservation of momentum. That's linear momentum. So when I say momentum, I usually mean P. If I mean angular momentum, I'll do it this way. And now I choose the obvious point of rotation, in this case, the center of mass of the rod clay system. So here it is. Mass of the clay, velocity of the clay times r perpendicular. R perpendicular is going to be d/3 in this case, because it's the impact parameter relative to the rotation axis, which happens to be the center of mass. Whew. And then here's the moment of inertia. And then, so you could actually get the final rotation rate. And then you could do the percent. Okay, oh my gosh. All that work done. Woo! This is a little bit crazy. Now, I want to show you something here in the solutions first. Ooh, I love this one. If you could do 11.11 and 1/11th, you know your shit. Okay, let me skip this. Let me skip this. Let me skip this. Let me skip this. I'll come back to this in a minute. Oh, secret suitcase. All right. Let me show you something really quick, just because we're at a good spot to talk about it. So far, we have discussed 3 different conservation laws, and this is page 93. Page 93. What is the point of a conservation law from a big picture? Conservation laws allow physicists to relate a before to an after, right? If you could properly identify which conservation law applies, you will write down a correct equation that applies to a before and after picture. That is somewhat useful to apply equations correctly. So it's not enough just to grab an equation. For example, conservation momentum. If this is true, then you can write it down. If this is true, you could write down angular. And then if this is true, you could write this down. That is the big picture from this entire semester. Obviously, knowing the big picture without knowing how to do the nitty-gritty details is approximately worthless. So it's not enough just to know this table and think you understand physics. However, it's not enough just to know how to flip some equations around either. It's the combination of knowing when you can apply these conditions and how to apply them. And so the rest of the questions from this point on, from page 93 on, it's just rapid fire practice. Which ones apply in a bunch of different scenarios? And you could see, okay, here's a bunch of different, you could imagine these look like different test questions. And yeah, so you could see which of these apply for a lot of the various cases that we've seen. So, all right, remember this one? We did a problem like this. You think you could do angular momentum on this problem or not? 11.29. Let's take a look. Does this look like an angular momentum problem?
No.
No, it looks like a chapter 9 regular momentum problem. Turns out you could do it with angular momentum. It's just not the smoothest way to do it. Angular momentum could do, and you would actually, if you used angular momentum, both of the impact parameters are identical. You actually get the same answer. You get back to linear momentum in one line of algebra. So So anyways, you could see some of these other ones. Oh, here's a different one. Yeah, okay. All right. I keep hinting at you to try coding these, but yeah, there's that. All right. Now it's almost time to go. I want to end with something slightly fun. Give me a second here. All right. Sorry, almost there. All right, let me see if I have it here. All right. Oh, let me do this too. I'm going to share, and I don't like to usually do this, but I'm going to share with the volume because you guys are probably broken right now. All right. And so we're going to look at this one. And I know you're tired, but I just thought we'd try this one out.
All right, here is the setup.
Are you guys able to hear that?
Yeah.
Okay,
Yes.
thanks.
Have a rifle mounted vertically, and we're going to shoot a bullet into this block, right into the middle of it. And so obviously the block is going to go flying into the air. But we're going to do this again, and instead of firing the bullet right into the middle of the block, we're going to shoot it off to one side. And I want you to make a prediction. Will that spinning block, when we hit it to one side, will it go the same height as this first block? Will it go not as high, or will it go higher?
Okay, so versus being shot in the middle when you shoot on the side is the question, right? Like,
Yeah, how high will it go in
height.
comparison?
It depends on if the bullet stays in the block. And I'm assuming it does.
It does stay in the block,
It
yeah,
does stay
I'll
in the block,
guarantee you
okay.
Same height. I'm purely basing it on just like an instinct that I have.
I feel like I'm being tricked.
that. I just feel like you're trying to trick us and that it's going to do something that we can't predict.
I feel like the obvious answer is not as high, so I'm going to say higher.
I'll say higher, but it's going to like fly in a different direction or something.
So you have angular momentum, which
Yeah.
is L,
Yeah.
and you have translational momentum, which is P.
Yeah.
When you hit it in the middle of the block doesn't really spin at all, so it just goes up to a certain height. But when you hit it on the side of the block, it's going to be spinning, so it's going to have imparted some kinetic energy, so there won't be as much potential energy.
And so the total energy of the system,
Basically has to stay constant, and the kinetic plus potential, which would be the height it goes to, will have to be constant. So if it's spinning and has kinetic energy, it can't go as high. That's my prediction.
so my prediction is it'll go up, not as high, but it'll spin more if it's hit to the side. Am I wrong?
I want you to think, which do you think is the most reasonable?
What do you think, class? Go ahead and what are your thoughts? You could either dump them in the chat or you could just speak up. What do you think?
I kind of have a feeling that it's kind of similar to the problem we did earlier, where there's a string pulling with the same amount of force.
Right. Yeah. So that would make you think which answer here?
The same height.
Now, I just want to point out, Alonzo, you're suggesting the same height right here, and this guy right here is a NASA engineer, and he says not as high. Who do you think got it right?
A NASA engineer.
You. Yeah, boy. Yeah. I got this one wrong the first time I tried it too. It's the same. And you're exactly right on your intuition. Isn't that cool? So look at all, this is a very easy one.
Reasonable, and then click one of the annotations above.
I think it'll go right to the video
Are
if
you
I
ready?
just play.
Make your prediction in 3, 2, 1.
Nice job, Alonzo. At some point, I think it changes. Sorry.
That face that is usually covered by her phone has finally made an
Oh,
appearance.
geez. Ads. Where'd the video go? Where is it? Did I screw up somehow? Oh, there we go. Sorry.
We were
another ad.
Facebook.
All these freaking ads. All right, here we go. Whoops.
Performed an experiment in which 2 identical wood blocks were shot with the same rifle. One through the center of mass and the other one slightly off to one side. Now, if you haven't seen that video yet, then click here now and go and watch it. Or if you're on a mobile device, click the link in the description.
Do they do this somewhere?
So the question was, compared to the block shot straight through its center, how high would the block shot to one side go? Now, 60% of you predicted,
All right, hold on.
but some of you may say, okay, well, there's also
Wait a
angular
minute.
momentum.
This is not the one I wanted to show you. This is not the one where they just showed the answer. Oh my gosh, I'm having trouble with YouTube. I feel like a boomer. Let's see. Let's see if I can get this one.
All right, here is the setup. I have a rifle mounted vertically, and we're going to shoot a bullet into this block, right into the middle of it. And so,
Maybe I have
One.
to click. There we go. Now, if I click that prediction, will it make it go to the right one? Is it right here? There we go. Come on.
What are you doing?
Guys, I'm so sorry. This is keeps putting up ads.
Those are for you.
All right, let's watch it.
There we go. Got
Hopefully
it.
I'm not horribly wrong. Derek's giggling to himself right now.
okay, you have made your prediction. Now it's time to find out which block went higher, the one that's shot off center or the one that shot right into the center of mass. Okay, we're just getting set for shooting straight into the block. How you feeling about this one, Dave?
I think this is the one. I really do.
Okay, range is going hot in 3, 2, 1.
We've moved this block, so now the gun is actually firing into the right side of the block. So presumably, one imagines that the block will spin anti-clockwise.
3, 2, 1.
Cheesy music. Sorry about that.
Now check out the high-speed footage. You can clearly see that both blocks go to the exact same height, even though one is rotating. And that's a bit strange because they were both hit by the...
All right, so we finally made it to the video clip. What the heck is going on here? Let me see if this makes sense to you. So just like Alonzo said, here are the problems that discuss this. So 10A and 10B, and apologies for me being bad at the video. If you do the change in energy, look at this extra term that shows up. So if I do just the straight problem from chapter 9, I get the change in energy is this. Now, this term right here and that term right there are essentially the same. But notice you have some extra energy, so you don't lose quite as much. The idea here is when this thing hits, it's able to give a bit during the collision, just like when you pull this thing As you pulled it, the rope was able to give, and so you had to pull hard. In effect, let me see if I can do it like this with my hands. When the bullet hits it straight in the middle, the entire system goes up. When you hit it on the side, it's going to start rotating, and as it rotates, because the wooden block is moving upwards on this side, it will extend the amount of time over which the bullet is in contact. That reduces the amount of force required. The bullet doesn't go as far in, it doesn't lose as much energy to heat. I don't know if that made any sense at all, but that's class for today. So for next class, we have a quiz on chapter 10. Anything in chapter 10 is fair game. And so be ready for that. And we'll finish up chapter 11 next time.